Thank you very much. So first of all, I would like to thank the organizers for this very nice conference. It's always a renewed pleasure to come back to Cargèse. The weather is super nice, especially pleasant in this pre-summer period where the weather is not that warm, I would say. Okay, so let me come to the topic. So today I would like to discuss about our recent works on the out-of-equilibrium dynamics of correlated quantum systems. So here you have an example of a calculation of the evolution as a function of time and distance of a spin-spin correlation function in the long-range Heisenberg model. And then you see a complicated behavior with age here that is usually called a light cone, and some complicated dynamics inside this cone. So this is what I want to discuss today, essentially. So let me first thank my collaborators. So this is the work of generations of postdocs and PhD students. So I would like to acknowledge in particular the work of Julien Després, Lorenzo Cevolani, Louis Villa, Jan Schneider, who were PhD students in the group, as well as Giuseppe Carleo and Stephen Thompson were postdocs and contributed a lot to these topics. I would like also to acknowledge some nice collaborations we had with Luca when he was in Barcelona. He's now in Madrid. Okay, so the question I want to ask here is relatively simple. So the question is simple, the answer is more complicated, of course. So you take essentially a many-body system, a quantum system, whatever it is, so you can put essentially whatever you want. And then the question is, what happens if you start with a state that is not a stationary state of this system, that is not a non-eigenstate of the Hamiltonian, and you want to know what happens as a function of time, essentially. So in principle, the question we ask here is very simple. I do not consider any interaction with the rest of the world, and then the system is isolated, so in principle, I can solve my problem through the Schrödinger equation, knowing the Hamiltonian of the system. So, of course, this is a very oversimplified statement. In particular, if you don't know how to diagonalize the Hamiltonian, it can be a nightmare. And even if you know how to diagonalize the Hamiltonian, it's a different question of asking what is the microscopic dynamics of each eigenstate and knowing what is the overall behavior of the system, of course. So these questions are related to three main questions. The first one has been already discussed yesterday by Nicolas, as well as in this morning by Emanuele. So the first question you may ask is whether the system will relax to a stationary state, maybe a sumal equilibrium state or an effective local sumal equilibrium or not. So this is related to ETH, many-body localization, and these kind of problems that I will not address here. So I will rather focus on these two other questions. In particular, we may ask if you perturbate the system at some point, then how information will spread out in your many-body system. This is related to the second question here, is what insight we can gain from the dynamics of the system about its microscopic properties, and in particular, the spectrum of excitations in this system. So these are the two topics I want to address here. So to do that, there is a very useful tool that has been developed, in particular in the context of cold atoms, which are quantum, in brackets, quenches, which consist in changing the system abruptly at some time t equals 0. You have several ways to do that. So you can either change the states through some kind of unitary evolution or maybe a measurement, and then the state is no longer an eigenstate of the Hamiltonian, or you can do it locally, you can do it globally, or you can, vice versa, change the Hamiltonian without changing the state exactly at t equals 0, and then after, for positive time, the system will evolve. So to be specific, I will focus on global Hamiltonian quenches. So this is essentially the picture I have in mind. At negative time, the system evolves for an initial Hamiltonian, then you cool it down to the ground state, and then at time t equals 0, you change some parameter of the Hamiltonian, which you perturbate globally, homogeneously in this case. Then at time t equals 0, the state doesn't change, but then it starts to evolve at a later time. So that's the idea. So this kind of picture is usually, or method, is usually well adapted to studying the problem of relaxation. It may not be that straightforward to study a propagation of information, because if you have an homogeneous system and make an homogeneous quench, then your local observables can evolve, but you will never observe any propagation. Nevertheless, there is a way to observe a propagation, is to get a look at correlation functions. So I will focus on a generic correlation function that is written over here, that I usually call G, that depends on the separation between 2 points. It evolves in time. And then this is written as the product of 2 operators that I call O1, dagger, O2, that are local observables, one at position 0 and the other one at the position R, and I let the system evolve. And then the question is what will happen to this kind of system. So this is a kind of things that have been developed in, as I said, in cold atoms. One, so just to have an idea of the picture, you can imagine a Bose-Hubbard model, or any Hubbard model, that is realized by a periodic lattice with some atoms inside, and then you quench the amplitude of the lattice by changing the intensity of a laser, for instance. Okay, so there is a rich physics. This is a problem that has been widely studied, but actually there are just a few experiments looking exactly at the propagation of correlation. So one has been realized in a group of Emmanuel Bloch quite some time ago, where they realized exactly a Bose-Hubbard model by quenching the amplitude of the potential, and then they measure kind of density-density correlation. So there are some subtleties, but essentially it's this. And this is the correlation function that is measured at different distances as a function of time. And what they observe here is a propagation of a signal. Sorry, time is running in this way, so the propagation is in this way over here. So this was the first observation of this kind of topics. I would like to mention that here there were some subtleties that were overlooked. In their case, it's not that important, but I will show you that in general it is super important. Another kind of experiments that have been done are in long-range systems. So the typical models are spin models that are interacting with an exchange that decays algebraically as a function of the distance. So this has been realized in a group of Chris Monroe in particular. So here you have some results of a propagation as a function now of position and time vertically. So position is horizontal and time is vertical here. And so they realized these spin models in ion chains by engineering some long-range interactions, and they observe a propagation of correlations. There is another work in the group of Rainer Blatt, exactly at the same time, where they observe the same kind of things. The system is a little bit different. In the case of Monroe, it's XY model. In the case of Blatt, it's Ising model. And they observe the same kind of propagation as a function of time. So what is important to mention is that, to be honest, their systems were very, very small. So essentially, there are 15 sites, 15, 20 sites in the problem. So it's very difficult to infer what is a propagation of a long-range model. Even more, it's difficult to define what is the long-range interaction in the system, because if you have 15 sites, essentially, you can fit any long-range correlation by a power law with more or less the law that you want, the power that you want. So this is a bit too small to really infer some dynamics, and I will discuss this problem from a theoretical point of view. Okay, so here I was a bit fast. So what is known about this kind of problems? In particular, there are some bounds that are usually called the Lieb-Robinson bounds that, so bound by definition, the propagation of correlations of different kinds in this system. So the typical picture in a short range system is that the propagation will be linear. So this is what you expect generally from short-range interaction. So the usual picture, again, is a position or distance horizontal, and vertically you have time here. So this kind of diagram defines a region, so a cone here that is usually called a light cone, where here you have some significant correlations, and here the correlation is essentially 0. So this is the bound. In long-range systems, in long-range systems, in long-range systems, some kind of bounds have been developed, in particular by Hastings and Coma. There are various forms that I don't want to discuss too much here, but the usual picture is that your cone will be bented towards superballistic form. So this, remember that time in this is in this way, so a form like this is superballistic. So again, this is a bound, but the question is what happens inside the cone and what are the real correlations that you generate in this kind of systems. Okay, so there is another picture that is very fruitful, which is a so-called quasi-particle picture that is a bit more microscopic. And the basic idea was developed by Calabrese and Cardi, where they just have the simple idea that a local quench will generate a spray of quasi-particle at the position of this point. So here I consider a local quench first. So at a site I, so the quasi-particle will propagate with each their group velocities, and then at some point they reach a point B at a position R, and this will start to activate the correlation in the problem. So this gives you an activation time that is essentially the distance between the points divided by the maximum group velocities of the quasi-particles that have been generated in your system. So in my case, again, I'm considering, so this defines a light cone that is essentially at a velocity that is the maximum group velocity of your quasi-particles. So in my case, I consider a global quench, so the idea has to be developed a bit more. So the idea here is that a global quench will generate a spray of quasi-particles at each lattice site, as you can see here, and then correlations between a point A and a point B separated by a distance r will be activated at an activation time that is the distance divided by twice the maximum group velocity. And the reason is that in order to generate a correlation between these at this distance, you need that the quasi-particles emanating from A and B meet, and because you have quasi-particles from A and B, then the effective velocity is multiplied by 2. So the relative velocity is twice the maximum group velocity, and then you expect a correlation H at twice the maximum group velocities of the quasi-particles that you have generated in your system. Okay, so what we have done, in particular in this work, is to develop these ideas a bit further and get a look at what happens. So we start with a generic. So this will be totally generic. So this is my correlation function, which is a product of my two operators located at 0 and r, and then I compute it at some time t. So a little bit of math will give you a complicated, or lengthy equation, but that is very simple. So the idea is to take this operator here and introduce some completeness relations. So the first one is actually that I will write this average as a trace of the density operators multiplied by this product of operators. Then in the trace gives me a sandwich of states that are that I call n prime on the left here, and that I will recover on the density matrix on the left of the density matrix here. So this is the term that appears here. Then I introduce a completeness relation then in the middle of, in between rho and O1. So this will give me one term of the density matrix, so which is the coherence between the point, the state n prime and the state n in the initial state, just before the quench. And then the rest here, so I recover on my operators NO1 dagger. Then here I have another completeness relation, again a m, that is subjected to A2, and then the n prime that comes from the trace. Okay, so this is a bit lengthy, but it's useful. In particular, you have two important terms that appear here. So the first one is the time evolution that comes from the evolution of the density matrix. For the terms n and n prime, so here you recover the exponential of I times the energy of the state n multiplied by time t, the opposite for n prime because it is on the left here. And these terms comes from the translation of this operator. So I have an operator that is located at r, and I translate it back to 0. So this is what I call O1 dagger. And then here I have the generator of the translation that comes as a difference between momenta of m and n, of the state m and n, that appears here because this is a translation of O1 only, multiplied by the distance. Okay? So this is essentially the picture. There is another term that is super important, that will save us actually, is the fact that my system is globally invariant. So if my system is globally invariant, I have to conserve the overall momentum, which means that the initial state and the final state must have the same momentum. So this is the thing. So you see here that actually the propagation is completely encapsulated in this term, and these are coupling terms, which in general will couple all the states of my system. I should mention that, of course, I work in a basis of state, of eigenstate of my Hamiltonian. This is what allows me to write this time evolution as just this exponential. So essentially what this complicated equation tells me is first a conservation of the global momentum, a propagation that is not completely simple in the sense that the difference of energy is between the states n and n prime, while the translation here is between the state n and the state m. So this will complicate a bit our life, but this is what it is. And then the rest are just coupling that in general we may expect that they couple all the states for generic observables. Okay, so a little bit of simple assumptions will now allow us to write a generic form of this correlation function. So the first idea is that we'll restrict to a weak quench. So the idea is that we will stay close to the ground state, which means that either n prime or n has to be the ground state. So it means that we'll just get a look at coupling between the ground state and some of the excited states that are over here. The second important assumption I will make is that these operators are simple operators and are just able to generate or destroy one quasi-particle and not more than that. So this may look a strong approximation, a strong hypothesis, but in practice, for many systems, this is what happens. You generate, each operator is just generating one quasi-particles or destroying it. Okay, and then this was the third assumption. The second assumption is that my excitations will be fully described by their momentum. So I have an homogeneous system, so they have a well-defined momentum. I will just assume that there is one single particle at k. You can extend the calculation that I have mentioned. If you have just several energies at the given momentum, it just complicates the math, but it doesn't matter so much. So with this simple equation, you get an equation like this, which is very simple. So you have a first term, which is just the term coupling the ground state with itself. So this is a boring part where you just have the correlation function at time t equals 0. And then you have another term here, two other terms here, that come from this propagation. So the idea is that you start, for instance, from the ground state. This operator will generate one excitation with a momentum k. Then this one will generate a second quasi-particle with a k prime. But I have to remember that I have to conserve the full momentum. So this means that the only thing I can do is generate a k and a minus k. So this makes the connection between these two terms, actually. So here you have the generation of 1k here. Pn is 0 because this is my ground state. And here I have generated two quasi-particles with k and minus k, which have the same energy. And this comes with a term that evolves in time as twice the energy of this quasi-particle at k. So if you do your math properly, then you have two terms, one propagating in one direction and the other one propagating in the other direction. Okay, and then this term here contains a lot of information about these couplings and the initial state of your system. The rest is in the propagation and come from this term here. Okay, so what can we do with this? So now, in order to evaluate this correlation function, what we can do, so this is a standard calculation, is to recognize that these terms are oscillating very fast, except when the phase is stationary. That is, when you change k, this phase remains at a constant. And then you can compute essentially everything. So the calculation is here. You look at when your phase is stationary. So this gives you relation between the ratio of the distance between the particles and the time, that is twice the group velocity at some momentum k. So this momentum is the one that is that makes the phase stationary for this ratio of the position and the time. And then you can just expand this up to second order, and then you get the standard calculation that will give you the correlation function with an amplitude here that comes from the integration of the second order term in this expansion, and a cosine of k times r minus 2 the energy at the stationary momentum multiplied by time plus one phase. So in the case, so this gives me a twofold structure of the correlation cone. So the idea is here, this is a typical excitation spectrum of quasi-particles in my system. There may be a gap or not. And I assume that I have a lattice system, so my momenta are bounded in the first Brillouin zone. Okay, so what do I get? The first thing is I need that there is a solution to the stationary phase, which means that the ratio of r and t should be smaller than twice the maximum group velocity, that should be around here in this example. Otherwise, this amplitude will be simply 0. And this defines exactly the cone that is generated by the maximum group velocity at some momentum k star. And then I get that I should find a linear cone at twice the maximum group velocity. There is another term here that is an oscillation of the cosine that will give me the dynamics of the oscillations, so periodic oscillations of my system. And close to the boundary of, so close to the edge of the cone, there will be governed by this k star, so where the group velocity is maximum. And this gives rise to an oscillation. And this oscillation propagates as the velocity, which is the phase velocity of my quasi-particles. So again, twice the phase velocity at the maximum of the group velocity. So this gives me a twofold behavior of my cone. So this is the theory. We have checked that through exact numerical calculation in various systems. So in particular here, I focus on the Bose-Hugbart chain. So we are working one dimension to have exact calculation with tensor networks, in particular time-dependent matrix product states. And then we have considered several quenches. So this is the phase diagram of the one-dimensional Mott insulator. And we make quenches, so either in a mean field superfluid regime, or in a strongly interacting mean field regime, or inside the Mott lobe, one of the Mott lobes. And then we computed several correlation functions, so either the one-body correlation function that is written over here, or the two-body correlation function that is written over here. And I will show you that this one has some peculiarities compared to the picture I gave you. So overall, there is a very good agreement with theory. This is what I have to show you here. So this is a calculation. So this is the Bose-Hugbart model at unit filling, scanning the ratio of the interaction to the tunnel coupling. So at n equal 1. So this is a case where you have a superfluid state. So we quench in the superfluid state. This is the one-body correlation function as a function of time and position. And then, so this one is a bit tricky to see, but nevertheless, here you are in the Mott insulator. That is still a weak Mott insulator. And here you are deep in the Mott insulator. So the overall structure is that, first of all, we see two features. So you have here H, where the correlations are very strong here and smaller here. I should say that with the beamer, it's not that easy to see that there is a threshold. But if you plot cuts at different times, you will see that there is a start of growing at the position of the green line over here. And on top of it, you have some maxima that propagate at a different velocity, which is exactly what we expect. In the Mott, case, you see the same kind of thing. So here it is a bit clearer in this figure, where you have a H here. Essentially, the correlations are 0 here. And here you have some modulations that propagate at a velocity that is different from the H. You have the same thing deep in the Mott insulator. So to be a bit more quantitative, we have fitted these two velocities here. So this is a plot of these velocities as a function of the interaction divided by the tunneling rate here. So we have these two velocities. Here is the transition between the superfluid and the Mott insulator in the model. And the lines here, so the dashed line is, a dashed line is the theory for the propagation of the local maxima, and the green line, the solid green line, is the theory for the propagation of the age here. So in here, this is based on Bogoliubov theory, and in this case, it's based on the Doblon-Holon pairs. So you see that it works very well, and the comparison between the numerics and the analytics is very good. Sorry again. So we have done the same calculation for G2. So for G2, we essentially observe the same phenomenology. The behavior is a bit clearer here, in particular in the superfluid. So you recover the two lines here, so propagation of the age, propagation of the maxima for the superfluid, for the weak insulator. And then we have fitted again for this correlation function the age and the maxima, and again it works very well with the theory. So if you are careful here, actually in the Mott insulator, deep in the Mott insulator, it doesn't work. So it doesn't work. We have the age, so it works very well, but we don't observe some maxima propagating at different velocities. The reason is that if you are deep in the Mott insulator, the ground state has, let's say, one particle per site, and then the excited state, I have one hole and one doblon somewhere. And this is completely orthogonal to the ground state. So and on top of it, if you look at the G2 function, so you are looking at the density, so you measure the density, so you never couple the ground state and the excited state. So my picture breaks down, and you have to go a bit further. So in this case, you have to consider the interferences between two doblons and Holon pairs in the system. So the machinery is a bit more complicated, but the idea is basically the same. In this case, what we find is that the correlation is the sum of two oscillating functions. One is a cosine square, and the other one is a sinus square. The sum of the two have no oscillation. So the oscillations are simply killed in the ground, deep in the Mott insulator. Okay, let me turn to, so this was about short-range systems. Let us turn to long-range systems. So my typical system will be the long-range transverse Ising model that is written here. So what is long-range is the exchange term between the spins along X, and then I put a magnetic field along Z, essentially, and then I will make a quench in the value of the magnetic field. So this is one of the models that have been realized in ion traps. They can also be realized in Rydberg atoms, although the exponent is not small enough in Rydberg atoms to have really a long-range behavior. Okay, so this is a phase diagram of the model, which exhibits three regimes. So essentially, this is the value of this exponent, so essentially the range of the interaction as a function of the ratio of and here the ratio of the magnetic field and with the exchange term. So essentially there are two phases, X-Néel phases when this term dominates, and a Z-polarized phase when this term dominates. And so this is well known, so when alpha is super large, this is here. So this is the short-range system, and when alpha is smaller, then you have long-range correlations, and then there are three regimes that have been identified. So when alpha is large, so large means larger than 2, then the spectrum is similar to the spectrum of short-range systems. So in other words, the long-range behavior is not that long-range, so you see essentially a behavior at short range. When the alpha is very small, so in particular smaller than 1, then in this case the excitation energies are not bounded. So you don't have a bound of the energy. And what is of interest for me is the intermediate regime for alpha between 1 and 0, where the energies are bounded, but the group velocity is not. So let me analyze the problem. So I come back to my generic form of the correlation function here. And now I have to deal with a more complicated excitation spectrum that in general we'll have a gap and then a behavior with k with some power that I take in between 0 and 1. So in order to have something that where the group velocity actually diverges at this point. So you can do the same math. It's a bit more involved, but the idea is the same as before. You identified for a given ratio of r divided by t what is the momentum where the group velocity is equal to r divided by t. So this goes, so the group velocity is the derivative of the energy with respect to k. So it goes like k to the power z minus 1. And then here in this case, so you see that I have a solution for any ratio of r divided by t, which means that contrary to the short-range system, I have to be a bit careful about the behavior of this prefactor over here. And in general, I will consider that this goes as a power law with some power nu, whatever it is. So this depends on the observable, and this depends also on the kind of quench that I will do. So if I do my math, I will find a structure like this. So again, you recover an envelope here that has a complicated behavior. So this is t to some power that is written over here. D is the dimension of my problem. Z is the dynamical exponent that appears here. And nu comes from the kind of, the behavior of this amplitude. And then inside, I have an oscillation of the cosine function in the cosine function that comes with a complicated function of the time and the distance. So specifically, well, you see that they are complicated exponents, and here you have a gap over here. So again, we find a twofold structure. Sorry, how I'm doing with time? Okay, so let me so let me show you how it works. So first, the age will be governed by this prefactor over here, and you directly see the behavior that t will go as a power of the distance. So in practice, this power, so the activation time will go as the distance to some power that I call beta CE. So CE is for correlation age. And this beta is just the ratio of psi divided by gamma. So in general, this behavior is subballistic, which you can infer from this complicated formula. So it's not that obvious, but if you make the ratio, you easily see that it is always larger than 1. So larger than 1 means that this H will be subballistic, which may be counterintuitive, because in a long-range system, you may expect something that is superballistic, but in practice, because of destructive interferences, it is subballistic. The other interesting thing is what happens for the oscillation here of the cosine function. And in this case, the behavior of the local maxima depends very much on whether you have a gap or not. So if you don't have a gap, so this delta is equal to 0, this behavior is trivial. You easily see that this will be a constant when t is proportional to r to the power of z. So remember that z is smaller than 1. So in this case, it means that if you don't have a gap, the behavior of the maxima will be superballistic. Okay, so the behavior is there a shot? Yes. So the behavior we expect is that in general, so this is the distance, this is the time. So I have a h that is like this, and then inside I have some maxima that propagate superballistically. So what I expect is a behavior like this. Okay? So you see that in particular, the behavior of the H is completely different from the behavior of the local maxima. One is ballistic, so superballistic, and the other one is subballistic. In the case where the system is gapped, then there is a delta in this case. So the calculation is a bit more involved. You can ask when r to the t divided by r to the power of z divided by 1 minus z minus 2 delta t is equal to delta t plus some constant. And then what you can do here is divide by time everything. So this is multiplied by 1 over t. So this goes to 0 when time is very large. I'm left with this equation. And then you may ask what are the coefficients here. So t comes with a power 1 minus z minus 1. And r goes like z divided by 1 minus z. So now what is this? So 1 divided by 1 minus z minus 1 is, so this is a t. This is a z divided by 1 minus z. That is exactly like r. So this comes like this, and this is a constant when t is proportional to r. So in other words, when you have a gap, the propagation of the maxima that are generated by this equation are actually ballistic. So in this picture, they will be simply linear. Okay? So let us get a look at numerical results again. So this is calculations for the long-range transverse Ising model in the z-polarized phase, and we quench the magnetic field. So this is an example of a propagation as a function of, again, of time and position. Be careful that this is a log-log scale. So linear means that we have power laws. Yes? So then we have played the same game. We have fitted the age, we have fitted the local maxima, and this is the result. So this case here is the case where alpha is between 1 and 2. So we have a true long-range behavior. We fit we fit the maxima and the age. This case is gapped. So this case is gapped, which means that we have a linear propagation of the maxima. So it means that the exponent is simply 1. And then for the age, we find something that is larger than 1, which confirms that we have a subballistic behavior. And it fits very well with the result of a spin wave analysis. Okay, so it works very well. We have also computed the velocity in the case of short range, that is when alpha is larger than 2. And again, it fits very well with a spin wave analysis. Okay, so this is completely consistent with the behavior that I mentioned. Now we have also looked at other systems or other cases. So this is again the long-range transverse Ising model, but in that case, I consider a local quench. So this quench will consist in flipping one spin. And then, so essentially we are in the polarized phase, so all the spins are up. I flip one spin, and then I look at how it evolves in time. So in this case, we find the same kind of phenomenology. We have, again, a twofold structure with a behavior of the age and the maxima that are different, and then we fit. And again, we observe that the age propagates subballistically. In this case, the maxima propagates superballistically. So the reason is a bit similar to the case of the Bose-Hugbart model that I mentioned, is that when you are deep in the z-polarized phase and you flip one spin, you go directly to the first manifold of excitations. And if you look at spin correlations along the z direction, you never couple the ground state and the excited state. So actually, everything works as if the system was not gapped, because everything works in the first manifold of excitations. And this is why we get a superballistic expansion of the spin, of the local spin, although the correlations behave differently. Yes?
Just a question about the plots. What are the error bars? Because you're doing the MPS calculation, did you sample over a lot of realizations, or is it some MPS?
Sorry, so this is MPS calculations, yes. So the error bars, well, I cannot tell you. So the error bars would be in the third direction, so I don't have them. But if you plot the behavior, you see something that is reasonably smooth, is what I can tell you. Okay, so I think I'm running short, so I will not mention the rest. Well, very briefly, we have also made some other calculations in other models that are really non-gapped, in particular, in the long-range XY model, and then we find, as expected, that we have a subballistic age and superballistic propagation of maxima. Okay. So the idea here, so this is the first partial conclusion, is that the light cone is generically displays a twofold structure, which is governed again by age that has its own behavior, and then some local maxima that have a different behavior. So this reminds you about, for instance, the swim of a duck in a lake, where you observe the same kind of thing. So you have an age here propagating at a certain velocity, and here maxima that propagate at a different velocity. So the first take-home message, let's say, is that be careful when you try to infer about the locality of this kind of correlation spreading. Do not look at the maxima, really look at the age. In the case of short-range systems, this is important because you don't get the right velocity. In the case of long-range systems, it's even more important. If you look at the maxima, you can have a completely different behavior. You may expect that the propagation is actually ballistic or superballistic, while the age, the envelope that really governs the propagation of information, is actually subballistic. Okay? So there is another, important message in this analysis, is that actually what happens close to the correlation age here contains a lot of important information about the excitation spectrum of the problem. In particular, in the case of a short-range system, it tells you what is the maximum group velocity and the associated phase velocity. In the case of a long-range system, the analysis of the local maxima and the age give you information about the dynamical exponent, but also the exponent associated to the quench and the observables you are looking at. So the question I want to address briefly now is whether we can do a better work. And actually we can. In fact, the space-time dynamics of this, behind the duck here contains essentially all the information about the excitations of the medium here. So in other words, the duck in principle knows everything about the excitation spectrum. So let me show you that. So the idea is very simple. We will essentially do a space-time Fourier transform of the correlation function that we have inferred previously. So I go back to my initial correlation function, and I simply make a Fourier transform over the position and over the time, and then I get this formula that resembles a lot the previous one, except that I have replaced the exponentials by some delta functions that peak here at a frequency that is the difference between the initial and the final energies of my system. So one is the ground state and the other one is an excitation of the system. So I should find a peak at the excitation energy. And here I have a peak in momentum at the difference of the momenta of this state. The subtlety again that is very important is that this energy difference is not the same. So the states that appear in this energy difference are not the same as those that appear in the momentum distribution. So nevertheless, if I do exactly the same assumption as before, assuming that each observable here, or each operator here, just generates one quasi-particle in a completely homogeneous system, I know that M will be one quasi-particle at K, and N prime will be a pair of quasi-particles evolving at a different, in opposite directions, sorry. Okay, so let me show that actually it works very well, and we can infer the excitation spectrum of essentially any many-body system. So again, we made exact calculations with tensor networks. Here is the Bose-Hubbard chain. So again, this case is a superfluid is in the superfluid mean field regime where the density is relatively large, the interaction energy is relatively small, and then we compute here the I think this one is the it's the two-body correlation function, which has a better signal, but you can do it also with the one-body correlation function. So this is what we get. And if we make a Fourier transform, this is immediately what we get. So we have here the frequency as a function of the momentum, and we observe exactly what we expect from a full Bogoliubov theory, where this is essentially a cosine-like excitation spectrum for free particles, except that here in the low K regime, you have this phonon regime that appears here, and you see that it works very well. This is the same calculation for now the Mott insulator regime, where the density, so we have one particle per site, a quite strong energy, and we compute the one-body correlation function. So this gives you this kind of space-time correlation pattern. You make a Fourier transform, and you find this nice excitation spectrum, which has essentially a gap over here, and then a sine function, which is simply the tunnel coupling between doublons on the one hand and holons on the other hand. So again, it fits very well. So the red lines here are just analytic calculations in the Bogoliubov approximation or in this doublon-holon pair theory. Okay, this is an example that I like a lot, which is a strongly interacting superfluid regime, where so we are in the superfluid, but the interaction is very strong, and then we vary the density. So this is a relatively small density, this is large density, and we play the same game essentially. And here you see that we observe a very nice feature that is very similar to what you expect in the Lieb-Liniger model. So for low density, this is what you expect. It is a bit, so you have these two branches of the particle branch and the Hall branch that appear directly in this spectroscopy. And so in principle, for a free system, you expect that it goes up quadratically, but here it is cutted by the discreteness of the system. And then you can compare to an approximate better ansatz. It works again very well. You can do that for, we have done that also for the long-range Ising model. So again, you have here your pattern. So it looks very, very messy. So a priori, it's very difficult to extract any information. But if you do a Fourier transform, you find a nice curve of the excitation spectrum that fits very well with the spin wave analysis. So if you are in a regime where the magnetic field is not that large, the spin wave analysis doesn't work, it breaks down. Nevertheless, the spectrum is typically the same shape, but there are corrections to the spin wave that you can observe here. So I have to stop, right? Okay, so this is kind of teaser, not more. We can also do that with disordered system, for instance. So it is a bit more tricky because, of course, a disordered system is not homogeneous, so K doesn't mean so much. But nevertheless, we can compute this Fourier transform, the correlation function. And then in a Mott insulator, you find a gap. In the superfluid, you find a nice photon branch that appears here. And in the Bose glass, you have here a blurb. I don't know how to call that, but at zero energy. So it shows that it is non-gap, and this is what you expect from a Bose gas. So this is a summary. So I will not repeat the first part that I already mentioned. The second important part is that these quenches and observation of the space-time behavior of essentially any correlation function up to subtilities in some special cases can give you all information about the excitation spectrum of the system and resolve indeed this transition for short-range systems, for long-range systems, as well as for disordered systems. Thank you very much.